Good morning to one all present here. Today I am going to present on the topic the examples of nuclear reactions. Nuclear reactions plays a crucial role in both natural and artificial processes. They are responsible for the energy of stars, the power of nuclear reactors, and even some medical applications. In this presentation, we will explore different types of nuclear reactions with examples. A nuclear reaction occurs when atomic nuclei interact or when a nucleus interacts with a subatomic particle, resulting in a transformation of one or more nuclei. Unlike chemical reactions which involve electrons, nuclear reactions involve changes in the nucleus. Because of this, they release or absorb enormous amount of energy. Nuclear reactions are crucial in many fields. They power the stars, enabling life on Earth. They also have important applications in nuclear power generation, medical imaging, and cancer treatment. We will now explore the different types of nuclear reactions. Nuclear reactions are categorized into several types based on how the nucleus changes. The main types we discuss here are nuclear fission, nuclear fusion, alpha decay, beta decay, gamma decay. Nuclear fission is the splitting of heavy nucleus into smaller nuclei, whereas nuclear fusion is the combining of two lighter nuclei into a heavier nucleus. The emission of an alpha particle from nucleus is known as alpha decay. The transformation of a neutron into a proton emitting a beta particle is beta decay. The release of excess energy in the form of high energy photons are called gamma decay. Now let's start with the nuclear fission. Nuclear fission is a process where a heavy atomic nucleus splits into two or more smaller nuclei. This process can be initiated by bombarding the nucleus with a neutron. Fission releases a tremendous amount of energy, which is why it is used in nuclear power plants and atomic bombs. Now let us look at some important examples of nuclear fission. A well-known example of nuclear fission is the splitting of uranium-235, where uranium-235 nucleus absorbs a neutron, it becomes unstable and splits into smaller nuclei, releasing energy and additional neutrons. These neutrons can further cause more fission reaction, creating a chain reaction. The principle behind nuclear reactors and atomic bombs. Another important fissile material used in nuclear reaction is the plutonium 239. Plutonium 239 is another commonly used fissile material. Like uranium 235, when it absorbs a neutron, it undergoes fission, that is nuclear fission, splitting into smaller nuclei and releasing energy and more neutrons. This reaction is used in nuclear weapons and some type of nuclear reactors. Now let us move to nuclear fusion. Nuclear fusion is a process where two light atomic nuclei combine to form a heavier nucleus. Unlike fission, which splits atoms, fusion joins them together. Fusion releases even more energy than fission and is the process that powers the sun and other stars. A key example of fusion is hydrogen fusion in stars. Inside the core of stars, hydrogen nuclei undergo fusion to form helium. This process, also known as hydrogen burning, is responsible for the immense energy output of stars like the sun. The fusion of four protons forms a helium 4 nucleus, releasing a huge amount of energy in the form of light and heat. Here are other examples. This reaction forms helium-3 and a neutron by releasing 3.27 MeV of energy. Next one is the tritium and a proton are formed with the release of 4.03 MeV. This is highly energetic reaction produces helium-4 and a neutron releasing 17.59 MeV. The last one is the reaction that generates helium-4 and a proton with a significant energy yield of 18.3 MeV. Now the alpha decay. Alpha decay is a type of radioactive decay in which an unstable nucleus emits an alpha particle, which is a helium nucleus containing two protons and 2 neutrons. As a result, the atomic number decreases by 2 and the mass number decreases by 4. Since alpha particles are relatively large and positively charged, they interact strongly with the matter and can be stopped by a sheet of paper or human skin. The examples of alpha decay are neptunium 237 into protactinium 233 emitting an alpha particle. Neptunium is an intermediate product in the nuclear fuel cycle. Then the platinum 175 can undergo alpha decay and become osmium 171. Then the other example is the gadolinium can undergo alpha decay to transform into samarium. In this process, gadolinium emits an alpha particle, reducing its atomic number by 2 and mass number by 4. Beta decay occurs when a neutron in an unstable nucleus transforms into a proton, emitting a beta particle. Beta minus decay and beta plus decay. In beta minus decay, a neutron converts into a proton, emitting an electron and an antineutrino. In beta plus decay, a proton converts into a neutron, emitting a positron and neutrino. Beta decay is important in processes like radioactive dating and medical imaging. Here the tritium consists of one proton and two neutrons. In beta minus decay, one neutron in the nucleus converts into a proton, emitting a beta particle, that is high energy electron. Since a neutron becomes a proton, the atomic number increases from 1 to 2, transforming tritium into helium 3. Now the gamma decay. Gamma decay is the release of excess of energy from an excited atomic nucleus in the form of high energy gamma radiation. Unlike alpha and beta decay, gamma decay does not change the number of protons or neutrons in the nucleus. It only stabilizes the nucleus by releasing energy. Gamma rays are highly penetrating and require thick layers of lead or concrete for shielding. They are widely used in cancer treatment and industrial applications. Cobalt 60 undergoes beta decay to become nickel 60. A beta particle, electron, and an antineutrino are emitted. The reaction releases 1.17 MeV of energy. The nickel 60 nucleus is left in an excited state. The excited nickel 60 nucleus emits a gamma photon with 1.33 MeV energy to reach a stable state. Gamma radiation is a high energy electromagnetic wave carrying away excess energy. In summary, we can say that nuclear reactions are powerful processes that transform atomic nuclei, releasing immense energy. They are responsible for natural processes like stellar energy production and have enormous application in power generation, medicine, and industry. However, challenges such as nuclear waste disposal and safety concerns must be addressed. With the advancement in nuclear fission, we have the potential to achieve a clean and limitless energy source for the future. The responsible use of nuclear technology is key to harnessing its potential for humanity. With advancements like nuclear fusion, we have the potential for a clean, limitless energy future. Responsible use and innovation are the key to harnessing their full potential for humanity. Thank you.